Right, hi, I'm not at school today, so this is my attempt at introducing this formally. You can take notes, but you can keep the clip, I guess. Going to look at a thing called the binomial distribution. It's what we talked about on Friday. I've got Steve Adams there as my example, and I looked up his stats, and I found that the probability of him shooting, of his shots going in, so the probability that a shot of his goes in happens to be 0.63 when he's playing for the Oklahoma Thunder. So the flip side of that is the probability that it's a miss would have to be 0.37. And you can't have anything but that. So the binomial distribution fits among the discrete ones because it's a whole number sort of thing, not a measurement sort of thing, and that'll make more sense as time goes on. But it's got 4 conditions, and you can see the conditions here. There has to be a fixed number of trials, so a certain number of shots put up per game. That fits quite nicely. Has to be a fixed probability. Well, we're assuming that this probability is always in place. So we're assuming that that's fixed. The trials are independent. That means each time he shoots, he's got the same probability of going in, and you could debate that. And there's only 2 outcomes. Now, that's certainly the case. It either goes in or it doesn't. You will find yourself in the questions having to justify choosing it. You won't be told this is a binomial distribution question. Your job will be to see whether it fits these conditions. Now, you could argue that it fits some of those conditions better than others. It fits this one very neatly. There are only 2 outcomes. And fixed number of trials, it fits very neatly because in a game, Steve Adams will take a fixed number of shots. The middle 2, however, the fixed probability, we'll assume that's true, but that's a little bit of an assumption because basketballers, like all athletes, have good games and bad games, and it might depend on the opposition and who's guarding them and that sort of thing. So we're assuming it to use the distribution, but there's a little bit of an assumption. Trials are independent. That's also a little bit of an assumption. Not a great basketballer myself, but like a lot of sports, you can get on a good run. And so you might get into a time when you're in the groove and the shots are going in, and you might later in the game have a bad spell. That could be related to being well marked or not, that sort of thing. So we're assuming it's a binomial distribution, and 2 of the conditions are great, and the other 2 require a little bit of caution, and that will be your job to make statements about that, having identified it. But at least it does definitely fit the first and the last, and they are the 2 that make it look like a binomial distribution. Bi meaning 2, so there's 2 things that can happen, a hit or a miss. Now, if we start with a reasonably simple situation, say he's only on for a wee bit, and so we want the probability that he gets 3 out of 4. Now, we can do a little bit of a listing approach to that off to the side, and we know from other probability that we've done that it makes good sense to list the things that can happen before you worry about the probabilities. Seen as a good technique. So we've got that on the go. There's 4 different ways it could happen. If we think about the probability of any of those ways, you could say quite comfortably that for each tick you've got 0.63. So if you've got 3 of them timed together, that's 0.63 cubed. Times, in each of those cases, there's 1 time the 0.37 slots up, and so that's to the power of 1. Now, normally I wouldn't bother writing a power of 1 in, but I'm a bit particular this time because I like those 2 powers to add to give me that magic 4. There is another 4, and this is a little bit of a coincidence in this case, but, well, not completely, but we have to times that by 4. And so we've got a situation where we have different numbers doing different jobs. This part here is number of, and we'll call this combinations. And my pen's letting me down, sorry. number of combinations. Ooh, not going well. Okay, so that's that part. This part here is when we're successful. I think I might have missed an C out of that, but that's all right. Success. And this part here, and this is to do with failure. Now, in terms of being able to calculate, if we change the question to likes of 4 out of 6, it's quite easy to adjust the powers. Then the 0.63 would be at 4 for 4 successes, and the 0.37 would be at a power of 2 for the 2 failures. What will become tricky is the number out the front. Now, there is a couple of ways of getting this. One is to use Pascal's triangle, which we looked at briefly in class the other day, and it starts like this and carries on down. In practice in this course, however, I don't reckon you're going to use this, because it comes with a formula that's on your calculator. Now, the way the calculator calls it is NCR. Now it has this formula that I've just put in, and it looks a bit fancy, but as a rule, we'll calculate this with our calculator. And so if you go on, we'll go to the next page, but if I go onto my calculator, I'll go the steps you would take. So on your calculator, you would be in the main menu, you're in the run mode, you go option. When you're in option, you look for probability, and you will see down the bottom the NCR will pop up. You'll put in 4 and then NCR button, and then 3, say, press equals, and you'll find you get your 4. So you could stall this and give that a try and check that it's working. Now, being able to do this allows us to scale the problem up. So Steve stays on the court a little bit longer this time, and so we want the probability that he gets 7 in out of 12. So we know that that's 12 shots. We're going to use the NCR button, so that's a 7. We know that his probability of getting it in is 0.63, so that's his successes, and we're working on 7 successes. Probability of a failure is 0.37, those two are complements. If 7 of the 12 go in, 5 of the 12 don't go in, and we've got those 3 things which you should think of as separate things multiplied together. So a binomial calculation, although the calculator will do it for you in one hit, you need to make sense of it. Number of combinations or orders that can happen, successes to the appropriate power, failures to the appropriate power, and that's what we'll get. So we'll run that through our calculator 2 ways. The other way to do this is to go to Stats from your menu, go to Distribution, which you will have done for normal distribution last year. You'll find one that's binomial. I think it looks sort of like that. Not quite like that. And you will go to BPD. P stands for particular. You'll see that there's a C there. C stands for cumulative. We'll worry about that later. So you go to BPD, and you will make sure this is your settings. I'll just go to the same thing myself, so just give us a sec. So the settings you're going to want when you're into BPD, you're going to make sure it's on variable. We never use stats in this course, and I think we talked about that briefly the other day. X is your number of successes. So for this one it will be 7. Num trial, num t, in this case is 12 because there was 12 trials, 12 opportunities. P for probability is probability of success 0.63. So what you should do now is calculate this the long way using the NCR button and calculate it the short way from you going stats, distribution, binomial and BPD, and check that you're getting the same thing just to test you got the calculator working right. Right, so in both cases you should be getting this. We usually write our answers to 4 decimal places in this course, in this particular standard anyway. So I've got 0.2163, or about 23% of the time. And so we've got that. Now, there's one last thing that we've got to deal with, so we'll go to another page and handle one more question, and then you'll be able to do plenty of practice from the book. Right, now let's go back to Steve. We'll stick with Steve, more appropriately, and let's say we want to find the probability that Steve gets 7 or more from 12. Now, for this, we're going to use the we're going to unashamedly use the calculator. And so I'm going to get you go back into menu, stat, go to distribution, go to binomial again, and we're going to use, for good reason, we're going to use B stands for binomial, C stands for cumulative, D stands for distribution. Now, there's a trick, and it's quite important. You may remember it from last year, but with cumulative, this part here, so I'm not sure I can spell that right, but I'll throw a couple of M's at it. Cumulative always starts from 0 up. Okay? Now, that's important. So it means we can't directly do this question. So we're going to have to do the classic 1 minus, which is a commonly used tool for the mathematician. And so, if we do a quick list, these are the things that could happen. 0, 1, 2, 3. And you don't maybe always have to do the list, but especially if the numbers are ridiculously big, you might just want to do part of the list. But we'll do it for this time. Just squeeze them in. Okay, so he takes 12 shots. There's the number that fit. Okay, there's the things that could happen, 7 or more go in means what we want is the probability of all of that. Now, we could work them all out individually, there's 6 there, and then we could add them up. But, better still, if we use the cumulative, we can find the probability of that happening. So if you go to B, C, D, and you go to cumulative, now we don't have to change too much because we've just done the last calculation, but what we want to do is this. So the probability, if X stands for the number of shots he's got in, probability of X being greater than or equal to 7, this is a little bit of probability speak, is equal to 1 minus the probability that X is less than or equal to 6. Now, that's a little bit of double speak on one level, but the good thing is a calculator can't do this, but a calculator can do this. And we can always go 1 minus, that's not a big problem. So, in a calculator, what we're effectively going to do is we're going to go first to, we're going to work this out. And then we'll do the 1 minus. So, I've got the same thing going on. I'm still on variable. I've still got, now my X is my number of successes, and I'm going to use 6. Num trial, which we'll call NT for short, is still 12. And the probability hasn't changed. It's still 0.63. That's not altered. So I'll just make that adjustment on my calculator. Now, if I calculate that, so basically do all of that, I get 0.2588 if I go to 4 decimal places. Okay. Now, if I leave that sitting on my calculator though, just go straight to menu, go to run, and go 1 minus, and then use shift to get your answer. Because that's the last thing we just calculated, and I press it, it'll do the 1 minus for you. Now you might be able to comfortably do that in your head anyway, but it's quite a good thing to keep in mind that it does record that as the most recent answer, and 0.7412 is the chance that he gets 7 or more from 12. Okay. Now, just before we knock off, and I'll let you get on with the practice, and the practice starts on page 132 in the book, and there is many examples. So if you try and do at least sort of 4 or so, and then we'll pick up there when I'm back the next period. So let's say it's page 132. There's plenty of explanation before if you want another opinion other than mine. But here's just the last thing. If he takes 12 shots, how many do we expect him to get? What's likely? So the expected, this is just something to keep in mind. What we would take the number of trials times the probability, and this is good inherent logic in this case, 12 times 0.63. So if I go 12 times 0.63, 7.56 is what we expect, and that's why the probability for this is quite high. If we made a graph of this distribution, then we would expect it to be more likely around 6, 7, 8 would be the higher bars, and it would get lower as you went either side. And so that's what we call, so out of 12 shots we expect him to get 7.56 on average. Okay, although he never will. Now I hope this works and is clear. And go to page 132 in the workbook. There's 3 good examples. Remember, if you want a particular value, just one off, it's BPD. And if you want cumulative, you have to accept that it works from 0 up. It's fine if that's the way the question's worded, but if it's not, you're going to use this 1 minus idea. Okay, thank you.